Hello and welcome to CMG's webinar on Reduce Your Risk by Quantifying Geological Uncertainty through Brownfield Optimization and Probabilistic Forecasting. My name is Anjani Kumar. I'm the Vice President of Engineering Solution and Marketing at CMG. I'll be the moderator for today's session. I'm pleased to introduce Jason Close, Canadian Regional Sales Manager at CMG, who will be presenting today's webinar. Jason has been with CMG for over a decade, with experience in North America and Southeast Asia. His expertise includes heavy oil and EOR technology with an emphasis on machine learning and optimization. He holds a Bachelor of Science degree in Petroleum Engineering from Colorado School of Mines and is a practicing professional engineer. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. Over to you, Jason.
Good morning. I thought we could start off the day with a quote from John Maynard Keynes. I'd rather be vaguely right than precisely wrong. This quote can raise many debates, but in context of today's talk, I think that unfortunately reservoir engineers, and specifically simulation-focused ones, have a reputation of being precisely wrong when it comes to production forecasting. I'm a reservoir engineer by training, and in over a decade at CMG, I've seen that quite often decision makers at our customers discount simulation forecasts as being very precise, but not very accurate. They do see value in simulation for learning through sensitivity analysis, but do not tend to trust the forecast. So why is that? Well, understanding uncertainty is critical to business success, and quite often our simulation models are deterministic in nature, and as such, ignore critical uncertainty. In today's market more than ever, quantifying uncertainty is crucial. What I would like to show you today is that through CMG's ongoing development, we can help you easily carry geologic uncertainty through your workflows, and by carrying this uncertainty through the workflow, we can improve the confidence in forecasting and can provide immense value in making better decisions. To illustrate this, we will go through a conventional waterflood case where we will introduce some new approaches. We will cover the full brownfield life cycle. First, I would like to introduce a new approach to history matching, followed by an introduction to probabilistic forecasting, and finally, we'll do robust optimization where we optimize under geologic uncertainty, and through each of these three sections, we will carry forward our waterflood model. So I'd like to rephrase Keynes's quote. Would I rather have one precise history match or a range of plausible solutions? Obviously, we would like a range of plausible solutions, specifically if they encompass our uncertainty. But generally, we take a deterministic approach to history matching and end up with one precise solution. This is not only by choice, but also due to limitations in technology. Ideally, we not only incorporate uncertainty into our model, but also effectively search our uncertain space. To search this space effectively, CMG has developed a new method of history matching using a Bayesian engine. Well, what is a Bayesian engine? We talked a lot about Keynes today, but we're going to go even further back into history and talk about Thomas Bayes. Bayes theorized a way to define a posterior probability density function, also known as a PDF, by incorporating the misfit between predicted results and measured results. It takes a statistical approach to history matching. We compute a probability density function of parameters taking into account simulation modeling error and the actual measured data. Then we cast this into multidimensional space, and we can understand how well our model matches results. But we can also use this function to interpret patterns and look for non-uniqueness by finding other well-matched models. So how do we go about using this? We need to cast Bayes' theorem into a multidimensional case. And a widely accepted form of Bayesian engine is the Metropolis-Hastings-Markov chain Monte Carlo method, also known as MCMC. This mathematical model uses Markov chain sampling to correlate nearby samples. Then, by taking small steps, the algorithm searches the space looking for peaks and values that represent the largest variation in the response surface. So, more samples equals better accuracy. And therefore, this model requires a huge number of runs. Although this may be possible on simple mathematical problems, with complex reservoir simulation, it's just not very practical. So if this is impractical, what do we do? CMG has developed a new intelligent search model specifically designed to search for multiple matches, much like MCMC, but does so with significantly less simulation runs. we initially create a Latin hypercube experimental design, and we run those simulations to first broadly map a sparse space. Then we build a posterior proxy model from which we can generate random samples to estimate future posteriors. Once we satisfy Bayesian's posterior probability for one sample set, we run the simulation case and refine our proxy. We minimize the meandering from point to point that we see in MCMC by using the proxy to do the legwork, all the time improving our proxy performance by running additional simulations. In doing so, we are able to search the global space using orders of magnitude less runs than with MCMC. So how does this actually apply to reducing our uncertainty? I'd like to illustrate this showing you a simple proof of concept model with two parameters. Here we have a well test where we are trying to match the bottom hole pressure by adjusting the productivity index. Our only unknowns here are our permeability and our skin. First, we need to generate a truth model where we run 5,000 simulation runs using a brute force method. We have an appreciable subset of runs with an acceptable history match with an error of less than 5%, as you can see on the left. And on the right, what we've done is we've generated a cross plot of our skin versus our permeability. And what we see here is a linear relationship for our match models denoted in purple. What this illustrates is for this problem, the solution is very non-unique. Multiple combinations of skin and permeability can get us a good history match. Next, what we would like to do is test this same case with 4 currently available engines available in CMOST to see if we can get a match, but also to see how much non-uniqueness we can find in the solution. We see that in all the situations, we do get multiple matches when running only 100 simulation runs. And we can see that both the DE and the DECE method, both shown in the top here, get a significant sample of runs with less than 5% history match error. Now, if we generate that same skin versus permeability cross plot, what we see is that for all cases, we seem to hone in on a very specific spot in our uncertainty where the DECE is doing the best job of searching the space for non-unique matches. When we apply the CMG PAR method, though, we can see that because the algorithm is designed to specifically find the non-uniqueness, that we get a much better sampling of the non-unique match cases. We again see we have a significant number of history match cases shown on the left, but when we look at the cross plot on the right, we see that we cover the uncertain space much more broadly. So we can also illustrate this workflow now with a more complex model. And the model we're going to use today for our history match is the Brugge model provided to us by TNO. This model was originally developed to study closed-loop reservoir management and is an excellent case to use for our full Brownfield workflow. What I'd like to do now is take us to Results 3D to take a look at our base case model. What you see here is our model, and you can see that we're looking at our oil saturation. We have a typical anticline model, and you can see that we have a sealing fault near the peak of our anticline. In this model, we have 10 injectors located around the periphery of the oil zone, and then we have 20 producing wells. As we play this model forward, what we see is initially we have some primary production here in the area closest to us. And as the model moves on, what we'll see is some water injection start to occur, and we'll start to see the oil saturation drop as the water encroaches into our oil leg. This model has 10 years of production history and is about 60,000 grid blocks. We've been provided with 104 geologic realizations, and we have 8 different geological realization generation methods. So each different method is going to generate 13 unique realizations. So our history matching workflow is initially we need to rank and select representative geologic realizations. So we need to choose a subset from our initial 104 realizations that we will use for a history match. We'll then apply additional uncertain parameters, so other rock and fluid properties, and then we'll select the history match parameters, which will be our historic data, so our bottom hole pressure data as well as our rates. Then we'll run the CMG par engine to get our history match and try and understand the uncertainty in that match. To rank the geologic realizations for this specific case, we ran all 104 realizations initially and then plotted the oil production here versus the job. And you can see how we have the different 8 types of realizations presented by the 8 different clusters here. So what we'll do for our history match is we're going to choose the average case for each of these different realizations types to include in the history match. What we'll do now is we'll go to CMOST and we'll actually construct that history match case. Starting from the study manager, I'll just select our history match. And then we'll go directly to parameters. So under the parameters tab, what we can see is that we have our normal types of parameters that we would see in a history match, like our relative permeability data as well as permeabilities. And we're going to describe these as continuous functions. What you will see here highlighted in blue is that our first set is called realizations, and those are discrete values. What we have here is we've selected just the number of the realization, and that represents the include file. So each of these include files will be represented by one geologic realization. We then need to set up our objective functions. So we need to determine what sets our history match quality. And here what you'll see is we've set up our pressures as well as our oil rates and our water rates for each of our wells to be the matching parameters and an associated weight. Finally, we just need to set up our global objective function, and here it's going to be a very simple history matching error where we're trying to minimize the percent error. The final step before we can run CMOST is to set up our engine. And when I go to the engine, I just choose history matching, then the CMG Bayesian engine, and then I just choose the posterior sampling algorithm, which is CMG par sampling. So if you've been using CMOST for quite some time, you'll see that setting up this engine is very simple and similar to how we would normally set up any other CMOST case. Once we've set this up, we can go ahead and run the case, which we've already run prior to today's presentation. The first thing I'm going to do is look at our run progress. And here what we're going to do is graph our global history match error versus our run progress. And what we can see is initially is we have a large amount of variability in our search space. And we can see that this represents that initial Latin hypercube design where we're trying to search the overall space initially to try and find the uncertainty in the range. And then as we go through and we build the proxy, we refine on the different solutions. If I zoom in here, what we'll see is that we have a significant number of simulation runs with less than 6% history match error, probably close to 100. With our best case here highlighted in red, showing that we have about 5.1% history match error. If we're satisfied with the history match error, we can actually analyze some of the other data. What I'd like to do now is look at a cross plot showing our global history match error versus our realization. So this will help us to understand which realizations get the best history match error. And what we can see is that we have several history match or several different geologic realizations that do not provide us a history match error below 15%. So no matter what we do to the model, we just can't converge on a solution. If I zoom in here, what we can see is that below 10% history match error, we have 3 different realizations that get us good history matches. Interesting, if you remember the ranking of the geologic realizations, those actually represent the higher oil production cases. So what this is telling us is that the realizations which have a lower horizontal permeability overall are just not able to match the results no matter what we do. So this helps us reduce our uncertainty. But the question is, can we get a better history match error? So what we'd like to do next is do another history match run, and we'll take a subsample of cases that only include realizations from these 3 subsets. So instead of picking 1 realization from those 3 subsets, we're going to choose 3 realizations from those subsets and rerun the history match. So we'll go back to the history match, and under the parameters, the only thing that we have to change is the realizations that we're including. So instead of including realizations from between 1 and 100, we're just going to choose realizations that represent those 3 different realization types. So 30, 34, 35, 69, 70, 76, and then 93, 94, and 104. Once we've done this, our engine's already set up, and we can go ahead and run our simulation and analyze the results again. Much like before, we're going to go to the run progress and look at how our global history match error has changed through the course of the model. What you'll see initially is that the search space is much tighter, and we don't seem to have history match errors much higher than about 20%. I also see that we again cluster the results down towards below that 6% result. And if I zoom in here below 6%, what I see is that I have a significant number of runs below 6%, but I also have a large number of runs below 5.5%, probably just over 100 runs. And actually below 5% history match error, we have about 10 runs that get us a good history match, with our best run being at about 4.5%. Once we're confident with our history match, we can go ahead and do probabilistic forecasting. So we've satisfied our history match, and now we're ready to move forward to prediction. Traditionally, we would have taken our one best history match model and generated one deterministic forecast. We have no understanding of the uncertainty of the prediction, so how do we make an educated decision on how to move forward with this asset? But now that we've carried geologic uncertainty through the history match process, we should also include it in the forecast. In this workflow, we call this probabilistic forecasting. This way, we can bound our results with reasonable uncertainty, attempting to be vaguely right instead of precisely wrong. To illustrate this, we're going to go through another proof of concept for probabilistic forecasting. The case we're going to use today is the 9th SPE comparative solution project. This is a very simple model with a 24 by 25 by 15 grid. We have one water injector and 12 producers. Before we do the probabilistic forecast, we're going to have to go through a history matching exercise. And we're going to match permeabilities through permeability multipliers, 15 different multipliers, one for each layer. We're also going to adjust the KV to KH ratio for the entire model. And then also we're going to be adjusting different relative permeability endpoints. We perform the history match using both the DE method as well as the CMG par method. And we see that for both cases, we're able to get an appreciable number of history match runs with better than 5% history match error. However, since we know that the DE method doesn't do as good of a job searching the entire uncertain space, we really just don't know if the probabilistic forecast is going to give us a real understanding of the uncertain space. When we go ahead and we run those history match cases, what I see is for the DE model shown on the left, we have a large clustering of the results very near our base case. However, when I run this with the par case, knowing that we have a good understanding of our geologic uncertainty as well as our other uncertainty in our model, we can see that we have a much broader scope of uncertainty and results, which we can quantify and bound with our probabilistic forecast. So next, what we're going to do is we're going to apply this probabilistic forecast to our Brugge workflow using the CMG par sampling method. So we've already done our Bayesian history match using the CMG par method, where we did the experimental design, the RBF proxy modeling, and then the proxy-based accept and rejection. We filtered our history match results. So the results we're going to include are those with less than 5.5 history match error. So we've determined that threshold, and so we've identified those models. The final step is we need to set up our forecast well constraints, so how we're going to run the wells for the forecast. We have to forecast the simulations based on those acceptable history match models and then do the statistical analysis. So we'll go back to CMOST, and we'll go to the study manager, and we're actually going to set up our probabilistic forecast. So I'll select the history match that I want to use for the probabilistic forecast. And what you'll see over here on the right is we have a button that says Create Probabilistic Forecasting. So what I'm going to do now is I'm going to launch that wizard, and we can just follow the steps to easily set up our probabilistic forecast. We start with the best history match model, and then we modify the well constraints if necessary, and then we add the new dates and run the base case. So once we've done all that stuff, we select the base case data set from our folder. We then prepare the forecast CMM file. So we copy the history match CMM to the new CMM, and then we copy the well constraints and dates from our forecast base case from above to the new CMM case. And then we then just select this master set. Next, we need to choose how many of the history match solutions we're going to include in our probabilistic forecast. We can easily choose the best number of experiments here, either 50, 100, 150, and so on, or we can set up user-defined filtering criteria. And since we want to include data with better than 5.5% history match error, we're going to use the filtering today. So I'm going to insert a filter. We're going to choose global history match error. We're going to choose global history match errors less than or equal to 5.5%. As I hit next, what it does is it generates all the experiments that we have to run, in this case 138 runs, and I can quickly QC all those models to see what's included in the model. The final step is to go back to CMOST and adjust any objective functions we may want to change for the forecast. Once we're done, we can click Finish, and we've created our probabilistic forecast. We've already run our probabilistic forecast, so what we can do is we can go ahead and directly look at our results. What I'd like to do first is look at our time series data, where we can look at our cumulative oil production over the course of our 20-year forecast. What we see is that all the results around the history match are very clustered, which we would expect based off our 5.5% history match error threshold. But as we go out further in time, we see that we start to form a band of results. Fortunately here, we see that we have about 13% variability in our cumulative oil at the end of our forecast run. So when we're asked what we would predict our cumulative oil production for this field to be, we can very easily say that what we expect within a range of uncertainty, giving decision makers within our organization a much better opportunity to understand and weigh the uncertainty for decision making. We can do the same thing by looking at the cumulative oil production as well as other things like the water injection rates. The other thing we can do is we can actually look at the histogram for our field NPV. So if we don't want to just look at our production, we want to look at the net present value of the field, we can do that as well. So here what we're showing is a probability density function, which is denoted with the green bars. This shows us the frequency of the forecast runs that actually give us these different NPV values. So if we're asked, what's the probability of having better than $1 billion NPV for this field, I can quickly go to the cumulative probability plot, select 50%, and I can say that we have about a 50% probability of having higher or lower than $1 billion NPV. And we can do this for any of the different values, whatever the benchmark may be for our decision makers. So we can easily define not only our forecast, but the uncertainty in that forecast.
Before Jason goes into the optimization workflow, I'd like to pose a question to the attendees. A question will pop up on your screen, and the question is, which workflow do you use in your simulation production forecasting? And the options are deterministic forecasting, probabilistic forecasting, both, or if you don't do any simulations, then not applicable. We see a bunch of responses coming up as people are responding. We'll just give a few more seconds here and see the trend is, as expected, is leading towards deterministic forecasting. And out of the responses that we have so far, 41% attendees actually do deterministic forecasting, and surprisingly 32% do both, so which is pretty good. And 17% attendees do probabilistic forecasting. So definitely the number of people that have responded doing probabilistic forecasting is on the lower side, and I expect that after today's webinar there will be some additional information that will help you decide on what kind of forecasting is good for the work and the simulation you're doing and for the reservoir that you are studying. Back to you, Jason.
Thanks, Anjani. Once we've completed our forecast and we're happy with the results that we have, we then have the opportunity to optimize our future forecast. So traditionally, we would do something called nominal optimization. We would take our best history match model, much like in our deterministic forecast, and then we would try and find optimum operating parameters for that specific case. The challenge is that we made one critical decision on what history match to go forward with, and are we precisely wrong in picking that specific model? What we'd like to present today is a new method called robust optimization. Well, what is robust optimization? Through robust optimization, we try to minimize our initial assumptions by incorporating uncertainty into the optimization process. We do this by trying to find an optimal risk-weighted solution valid for any realization. Using robust optimization, a development scenario is verified using multiple representative reservoir models that cover our uncertain space. In the illustration here, we can see that we've carried three geologic representations through our optimization process, our P10, our P50, and our P90 case. What we then try to do is find one optimal operating strategy that maximizes the NPV or other optimized parameters for all three cases. And depending on how variable our cases, we may choose either 3, 5, or more cases, depending on our judgment. So what are the differences between nominal and robust optimization? Obviously, both have pros and cons. The pros for nominal optimization is that it is fast. We only need to do one simulation for each scenario. And regardless of the geologic uncertainty, we're likely to improve results. The cons, however, is that there's no guarantee of success, and we may be suboptimal in reality. And if we're not doing robust optimization or probabilistic forecasting, we really can't quantify how suboptimal we are. In robust optimization, the pros are we have a much higher probability of success because we're trying to incorporate geologic uncertainty, and we then have a lower risk. The cons, however, are that there's additional computation. However, this additional computation really is minor in the grand scheme of making better decisions. Much like the other concepts we presented today, I'd like to show you another proof of concept for robust optimization using a simple pattern water flood model. Here what we've done is we've taken a submodel out of a larger case with a inverted 5-spot pattern. What we're going to do is take our geologic realizations and try and understand where the optimal well locations may be for different cases. So we have 100 realizations, and then we're going to try and move the pattern through the model to try and determine what our best recovery factor is. So the workflow we followed is we generated 100 realizations. We then could use all the realizations, but instead we rank the realizations, and we're going to select 5 representative realizations to carry through our robust optimization. We'll use the robust optimization for those selected realizations, and we're going to try and maximize our recovery factor. Then we'll find our optimal well locations and apply this to all the realizations through a probabilistic forecast so that we can do our risk analysis and determine the robustness of our optimal strategy. Once we've completed this, we can analyze the results. What we're showing you here are some histograms for the different cases. So if I just take my base case well locations and run all 100 realizations, what I see is that my recovery factors generally cluster between 27 and 31%, with outliers as low as 23% recovery or as high as 36% recovery. If I take my P50 realization and run nominal optimization, what I see is that for most cases we do actually improve the recovery factor, which is fantastic. We see that we have less clustering, so there's more uncertainty in the results as we look at it within geologic uncertainty. We see that most of the results are between 28 and about 39% recovery factor. But we do see for our worst case, we actually get less recovery factor. So there is the potential in robust optimization, if we choose the wrong realization, that we could end up with worse results than our base case. Then, when we look at our robust case, where we've included 5 different realizations that we think encompass our geologic uncertainty, what we see is that we see a much better clustering of our recovery factors towards the higher side. We see that most of our results are between 33 and 40%, with even our worst case improving to 26%. So not only have we improved over our base case and our robust case, but we've also clustered those much closer together, which represent that we have less uncertainty in our solution. So when asked to make a decision, what we can see is that when we're looking at recovery factor, if we have a benchmark of a recovery factor of 32%, what I can see is for my base case, we actually have a 96% probability of having less than 32% recovery factor. After doing nominal optimization, we improve this greatly. We only have a 39% probability of having a recovery factor of less than 32%. However, by doing robust optimization, we can see that we only have a 9% chance probability of having a recovery factor of less than 32%. So doing both nominal and robust optimization, we can see that we greatly can improve our probability, and we can actually then, when going in to make a decision, we can actually scope out that probability and make an educated decision. When we go back to our Brugge model, we're going to now include the robust optimization for brownfields in our case study. So we've, of course, already done our history match using the CMG PAR method. We've filtered those history matches and done our base probabilistic forecast. Now we're going to take those filtered history match models, and we're going to select the base case for each realization that was included in the history match that get us good history match errors, and we're going to do a robust optimization. And then we'll follow that robust optimization with a probabilistic forecast. So we're going to go back to CMOST now, and you'll see in the study manager we have a little bit different look. And because we're using robust optimization, the workflow is slightly different. You'll see here we have a case with M, and this is our master study. So this is going to be the study that controls our dependent studies. So each dependent study represents a different realization model. And all of these are going to be rolled up into one optimization algorithm. So when I go to one realization, what I can see is that we've set up our net present value that we're going to optimize on. And then what we can do is we can actually go to our master study here. And then you can see that we have all 5 of our dependent studies. And then I can just sync the parameters, objective functions, and experiments for each case based off that first case so that we have consistency across the different cases. So we need to choose what mapped objective functions we're going to include. And so for each realization, we're going to include the field NPV as part of the mapped objective functions. Then we need to set a global objective function that all the candidates are going to have to be optimized on. And here what we're going to do is just select average NPV. So we're just going to roll up all those into one average NPV and run the optimization based on that. Setting up the engine is the same as we would set up for any optimization. We just choose that the study type is an optimization study, and then the method is the CMG DECE method. Once we've done this, we can go ahead and run the case and look at our results. What I see when I look at average NPV is that, remember that our sort of our P50 case for our regular forecast was about $1 billion. What we can see is we get significant improvement in NPV through doing our optimization. And we can see that quite a few of the cases cluster above $1.5 billion. This is quite interesting. But when we're doing optimization robust optimization, we also can look at box plots, which show us our average NPV. So here what I can see is I can see our best case as well as some of our other good cases, and I can see how the best deterministic case did and how the worst deterministic case did. So if I zoom in on this area, what we can see is we can validate that this is truly the best case, not just by average, but also it does the best for our minimum case, and it actually maximizes our best case to the highest level as well. So once we're satisfied with our robust optimization, we can go ahead and do probabilistic forecasting. So we've set up a probabilistic forecast for our new robust optimization case. We've already run that case, and then we can look at the time series data. What I see when I look at my cumulative oil production, based off our base case here shown in black, is that for most of the cases we've shifted them up. We only have a few cases that outliers that are below our base case. We do have a little bit larger range of uncertainty, so about 15%, but overall they're much better than our base case. If I then go down to our histograms for this specific case and look at our field NPV, we can again look at the probability density function. And then when asked, what's our probability of having better than $1.5 billion, I can go directly to that on the screen and say that we have only a 34% chance of having below that. So again, when we present this to management, we have the opportunity to not only give them our forecast, but also the uncertainty in that forecast. So here's a look at our cumulative probability for our base case and our robust optimization. We can see that we've shifted it quite a bit further up. We see that it's not quite as straight up and down, so a little bit more uncertainty across the range, but overall we've significantly improved our NPV for this case. And when we show this, it makes us very clear on how to make a decision. So I think, in conclusion, it's very obvious that in today's market, more than ever, quantifying geologic uncertainty is crucial. I also hope that you can take away that CMG has tools to help carry this geologic uncertainty easily through your workflows. And finally, through our case study, you can see how carrying this uncertainty through the workflow provides immense value in making better decisions. Just before we close, I'd like to come back to our quote from Keynes. I hope we can now agree how it may be better to be vaguely right than precisely wrong. Through the approach presented today, I think we have an opportunity not only to be vaguely right, but to quantify the uncertainty in our forecast and better understand the risk in our decisions. Ultimately, as a proponent of reservoir simulation, CMG strives to improve the reputation of reservoir simulation in providing quality, reliable forecasts.
Thank you, Jason. We will now take up questions. If you have any questions and have not already submitted it, you can do so now using the chat window on your screen. I see there are several questions that have been already submitted, and we'll try to take them one by one. The first question is from Zeno Philip, and he'll like to know is, when you talk about a match, are you talking about a particular value, say a cumulative oil or gas, or do you consider a least square error of multiple values in time?
So yes, we do consider the least squared error for the multiple values in time. So what we need to do is we select what pieces of our measured data we're going to include in the history match. So in our specific case, we included our cumulative productions for oil, water, and gas, as well as our injection, and our bottom hole pressures on both the injectors and the producers. And so we can add weight to certain periods of time, and we can include different parts in different periods of time, depending on the quality of the measured data.
The next question is from Kasif Saeed, and he'd like to know is, can we take into account a specific parameter in our objective function instead of a global objective function, suppose a combination of pressure and rates?
Yes, we can change the objective function depending on what's actually of interest to ourselves. So in our specific case, our Brugge case, we used NPV, but you saw that we used recovery factor for one of the base cases. But we can set up our objective function based off any of the parameters that you may be interested in.
The next question is from Youngwan Liu, and the question is how to set the numerical value for a different geological realization in CMOST.
Generally, we try and use the same numerical values for the tuning of the simulator for each case. So prior to doing these types of cases, we would do a numerical tuning session, and I believe that we have a training course on this that will help show you how to do this, as well as a previous webinar where we go through numerical tuning.
The next question is also from Kashif, and he'd like to know is, how can we make a sensitivity on different control modes, for example, well operating on different rates in a prediction run? What I can understand from the question is that Kashif will like to do prediction runs on different rates on which he like to optimize the production scenarios. So basically, what we are going to do is set up different operating rates as parameter for the well, and then do sensitivities by varying those rates as a sensitivity parameter, and then you can develop an objective function on which you want to assess the sensitivity on, whether it's cumulative oil or recovery factor, and then CMOST will generate those scenarios by varying the different rates in different runs. The next question is from Pawan Agrawal, and he'd like to know is, for different realizations, different optimization of well location and operating parameters can be done. So how can we choose my well location and constraint in future prediction, especially for a large field?
Well, this is the challenge, right? Is that when we do a geologic model and we have a lot of different realizations, which realization actually represents what we actually have in physical reality? And the challenge is even when the field is done, we don't probably even know what that is. So what we try to do in robust optimization is include multiple realizations that we think represent the variability and try and find one set that we can then apply, so that no matter what the actual reservoir holds, as long as our uncertainty is bound large enough that it includes the reality, we should be able to maximize our NPV.
And just to add on to that is regarding the well locations, when you do a well development planning for a particular field, you may have identified some possible well locations that you may want to drill in the future. So you can make all of those available to CMOST to pick and choose, and CMOST will actually activate or deactivate those wells if and when needed based on your drilling schedule, so that it can optimize on the objective function that you have defined. So CMOST has definitely that capability for queuing up future wells in your optimization workflow. The next question is from Kun Liu, and the question is, how many realizations are sufficient to have reasonable forecast results with relatively high confidence?
This is a bit of a challenging question. In reality, there's no unique solution. It depends on each asset, how much information you have. So if you have a lot of information on your asset and you've built your geologic realizations and there's not a lot of variability in the realizations, you likely could get away with using only 3 or 4. But in reality, we likely don't have a lot of measured data, so we need to try and include, in most cases, more than that, so that we can quantify the uncertainty. The challenge is that we need to make sure that we include enough that we adequately represent the uncertain space.
The next question is from Muzami Hussain, and the question is, how you rank your realizations for your robust optimization case?
For our specific case, we ranked our realizations. We did 2 looks at how we ranked our realizations. In one, we ran all the geological models initially beforehand because they ran quite quickly, and we were able to get cumulative production. What we also did is we looked at our average horizontal permeability for each case, and they correlated extremely well. So we likely could have gone ahead and used some sort of analytical correlation. So there's several different ways that you can do that as well out in the industry and in literature.
The next question is from Nelson Mann, and the question is, how to achieve optimization at well level using robust optimization. So what he'd like to understand is, if I do not have a variability in geology, and I have picked my realization with confidence, but I have variability in the well parameters, how do I optimize within the uncertainty of the well parameters? So basically what you're going to do is you'll fix the geological realization, but we do understand there is a lot of variability in operating parameters for a particular well. There could be operational issues, there could be issues related to different operating parameters for the well. So what you can do is in a robust optimization, you can make those parameters as uncertain parameters and define the ranges of those parameters, and you can use the same workflow. So instead of the geological parameter uncertainty, what you're going to do is make the production parameters from that particular well as variable and do the optimization workflow. The next question is from Stephen Faust, and the question is, am I correct in stating that if some of the realizations used for CMOST exercise correspond to distinctly different geological characteristics, which would require different optimized operational strategies, the optimized uplift is skewed to the downside? Now that's a loaded question, Stephen.
Well, there's a bit of a challenge, right? So in our specific case, what we did is we only chose realizations that gave us a good history match. So if we believe that we included all of our uncertain parameters in our history match, and we realized that just couldn't get us a history match, we should be fairly confident to say that those are not likely solutions. However, if we artificially choose the realizations that we include, we could skew the results.
The next question is from Sandra Fountain, and the question is it possible to incorporate geological realizations with different top structure interpretations, or are we limited to changing properties within a single defined box? That's a very good question, Sandra, because there is a lot of uncertainty in interpretation of the structure maps when you're actually generating the geological characterization or geological layering of a particular reservoir. So definitely what you can do is generate different surface structure maps, create different geological realizations with different structure maps, and then you can use those realizations in the same workflow that we just showed today. The next question is from Yungwen Liu, and the question is, after probabilistic forecast for each P90, P50, or P10 forecast, there are typical multiple simulation cases. Which simulation case do we actually pick? Well, definitely when you are using different realizations, you are actually looking at generating different forecasts under uncertainty, and you will be generating forecast which represents a range of forecasts which is ranging between your P10 to P90, and you have identified your P10, P50, and P90. All of those scenarios are, and you're actually allocating probability of those forecasts. So once you get more and more data from the field, then you can see which realizations and which forecasts are closer to reality, and then you can do conditioning of your forecasting depending on more data that you gather. So definitely it's an iterative process. Is none of the single forecast scenarios is we will recommend you to pick, but you have already assigned a probability of occurrence of those forecasts, and now it's a matter of correlating it with the real field data as you get more and more production and iterate on your forecast. The next question is from Guilherme, and the question is, could you provide more details on what kind of optimization parameters you had when running the robust optimization? Did you run one development scenario on various realizations of various development scenarios on various realizations? Or if so, how much control do you have on various development scenarios, just changing the rates, or can you change well counts, locations as well?
So for this specific case, we assumed that we weren't going to change the well count or locations, but we were only going to use existing wells. And what we did is we adjusted the rates and then the pressures within reason for each of the wells. So what we were trying to do was maximize NPV. And we did include multiple realizations for this specific case. However, if you wanted to include different wells, different locations, or even different EOR strategies, that can be included as well.
The next question is from George NG, and the question is, if you have a project stack, do you use the same selected realizations to determine incrementals? Now, we need to understand this question as it is not very clear, and also the attendee is not online at the moment. So we'll proceed with the next question. The next question is Kasif Saeed. How far is CMG with assisted history matching with MCMC and ENKF? Well, we are working on MCMC and ENKF, and definitely it's in the research mode, and we have some alpha version of CMOST that we are looking into. So definitely in the very near future, we will incorporate some of those new algorithms. So I think that brings us to the end of the question and answer session today. If we haven't been able to answer your question today, then we will be following up with you individually within the next few days. We will also be posting the recording of today's presentation on our website within the next 24 hours. So please log on with your CMG username and a password to access the material. So today, I hope you have gained a better understanding of some of the concepts related to robust optimization and how CMOS can be used with reservoir simulators to capture uncertainty and in the optimization and probabilistic forecasting workflow. CMG also offers a multitude of training courses for all skill levels. For those of you who are interested in knowing more about CMOST robust optimization workflows, we do offer courses on introduction to CMOST for conventional and tight reservoirs, and also a course on application of CMOST for thermal reservoirs. We also offer company-specific customized courses on a variety of subjects all around the world. For more information on some of these training courses, I'd like to invite you to visit our website at www.cmgl.ca. If you have any other questions related to the material presented today, or would like to know more about our product offerings, please do not hesitate to contact us at sales@cmgl.ca. Again, thank you all for joining us today for the webinar on Reduce Your Risk by Quantifying Geologic Uncertainty through Brownfield Optimization and Probabilistic Forecasting.